Good morning, BlueHat. It is Thursday and day 2 of the talks, and this morning we are opening up this room in Kodiak on the hardware track. To start that, we are going to talk about something that has came onto the scene, at least publicly, early in the year. It sort of consumed a lot of cycles for some of the people here at Microsoft and across the industry. Raise your hand if you're familiar with those now famous pieces of exploit. Spectre and Meltdown. Anybody familiar? All right. You're on the right talk then. Andrea is here today. He is one of our Windows Kernel researchers, and he's going to talk to you about Retpoline, which is one of the mitigations that was developed for the Spectre vulnerabilities. So with that, please welcome him to the BlueHat stage.
Hello, guys. Yes, today we are speaking about Retpoline, that especially how we have implemented in this mitigation in Windows. Okay, just a moment. Okay, now it works. So before starting, just 5 words about me. I am kernel software engineer in the Windows kernel-based team. I'm a Microsoft OS internal enthusiast and a security researcher. And I worked previously still in Microsoft for the Microsoft Threat Intelligence Center and before in the Talos group of Cisco system, like a researcher. And basically I did some research project, especially one that I wanted to speak about here very fastly is the first UEFI bootkit in 2012, the first available PatchGuard 8.1 bypass in 2014, and many others. And especially I was the first designer of the Windows PT driver. Okay, I need to apologize in the beginning because this talk was huge. So I have tried to concentrate the most important information, and I've divided in 4 pieces. The first one is it's an introduction about what is Spectre and Meltdown. It will be very fast. The second, we are speaking about the general architecture on the Retpoline implementation in Windows, and then we are going to deepen some details. So, speaking about Spectre and Meltdown. As you probably know, they are 2 of the most dangerous and effective vulnerabilities that have been discovered in all CPUs since around 1998. I will say almost because not all CPUs are vulnerable, but most of them. At the time of this presentation, at least 5 different variations have been publicly disclosed. 3 are the most dangerous. One side note, this talk is not about Spectre and Meltdown. Indeed, I'm not an exploiter. There are already multiple presentations that have been presented, and if you are interested in details, you can check those. So here I will try to go quite fast because we don't have a lot of time. For understanding the type 2 attack, we need to understand 2 things in the modern CPU. First is the branch target predictor, and the second is the cache. In this slide, there is represented the branch target predictor that basically works in this way. There is an indexing function that generates a tag, and from that tag, the CPU can predict the target. So it means that if you have an indirect call in an address, for example, in this case 9F, AAA 9F43AA17, the CPU stores the tag that is an index of the original address. In this case, this is Ashwell. It is an example. Basically, Ashwell uses the last 30 bits. And so in this example, say that the tag should be the last 30 bit. Of course, it's not correct because the 30 bit doesn't include the 8, but that is another story. And yes, for doing this attack, you need to reverse the branch target predictor, and can be reversed. The link that I showed in the slide is explain how people have reversed this architecture. So the second thing that you need to know is about the CPU cache. Even the CPU cache is first is like very fast volatile memory that is like reside in the CPU, and this usually is really fast. But its architecture is CPU dependent. So this is another example that is not actually true. Basically, like we have like an example of a 32-bit CPU. You can imagine the cache like a big array composed of rows, where each row is 256 bytes long. In this case, the address that could be like a physical or a virtual address is not important in this example, is composed of like a tag, a line, and the offset. In this way, the CPU can like store the data in a particular line and offset of like the cache. In this case, for example, the line is OX20 and the offset is 0, and uses the first like 16-bit as a tag. So the CPU store this tag. In that way, if like there is a cache collision, it can know that because the tag is different. These are the two basics that you need to understand for like you need to know for understanding the Spectre v2 attack. So let's see an example. In this case, there is a source process and a victim process. First thing that you need to know to attack using the Spectre type 2, you need to find a gadget. The gadget must be to access two arrays in a particular way. We will see in a while how. The point is that, basically, first what you do, you replace an indirect call, in this case like NT-set7, with an indirect call to your gadget. And you start to like train the branch predictor. In this example, I have written like the virtual address added by a delta and gamma value, because as we have seen, like the virtual address, it's important that the index is equal, not like that the virtual address is exact the same. But for this example, the virtual address, you can consider even the virtual address the same in source and victim process. So what you do, you like start to call the gadget using this indirect call. I mean, call NT-set7 a lot of times. In that way, you train the branch target predictor. After you did that, you need to raise the victim process to call the original NT-set7. In this way, the victim process, the branch target predictor, know to call the gadget instead of like the original set7. Then it understands that like basically the target is wrong and clear out the results. But the important stuff is that like the results are still in the cache. So here is like how need to be like the array. As you can see, there is a victim array that basically need to be like near like a secret value that you want to read. The attacker control the index. So if the index is out of bound, you can like read the secret like value that in this case is a character. There is even a multiplication by 256. This is because you need to pollute an entry in the cache. In this case, I have written 256, but basically the 256 is the cache granularity, so the size of the line of the cache. Usually 64 bytes, but this is not like the example that I did, because the example is 256. Higher multiples are used to reduce noise. So even if you use higher multiples, you can like pollute maybe one cache line, and then after 4 lines, you can pollute the other ones. It's not a problem. The important is that that value doesn't need to be like smaller than the cache line, the cache granularity. And yes, that's it. So basically, after you like raise the indirect branch of the victim process from the source process, you basically measure the access time of the probe array. The probe array must be like known by the attacker. Not exactly. This like sentence is not exactly true, because as we have seen, it's the virtual address. You need to only know how it's calculated in the cache. So you can basically, theoretically, you can even access like this, measure the cache access using another like probe array. Okay, I'm sorry if I've been too fast, but like as I said, this talk is not about Spectre. Basically, we got some conclusions. The conclusion is that the Spectre type 2 attack is effective even in kernel mode address space. One important thing about this attack is that the attacker could speculate only on indirect branches and not on direct one. If you have direct branches, this attack is useless. So basically, we needed a way to mitigate the CPU vulnerability, and we needed to do that in a, how do you say, in a smart way that doesn't destroy the performance of the computer, basically. So the possible mitigation. The first one is one like that is like has been like suggested by Intel using the indirect branch restricted speculation feature that basically disable the CPU branch predictor completely between different privilege levels and even on the sibling CPU thread. So this means that if you have like a physical core, and in that physical core is like hyper-threaded, so run two different threads, the IBRS disable the branch predictor even on the sibling threads. There are even other like possibility, like use IBPB and STIBP, that are still hardware mitigation. Or otherwise, we can use like Retpoline. So basically, the difference between IBRS and IBPB and STIBP is like are minor. Basically, STIBP disable only the branch predictor between like threads and not between different privilege level. And IBPB instead disable completely and flush the branch predictor buffer. But they are not important at that stage. So, Retpoline. Basically, we saw that in keeping the IBRS on all this most existing CPU has a very high performance cost. And so what we did, we render basically the speculation completely useless using like Retpoline. So basically, as you can see in this slide, basically let's assume that the indirect jump is jump RAX, simple. RAX contains the target of the jump. We replace the jump RAX with this code. This code emits like a direct call to the setup target. The setup target, what it does is simply replace the return address and then do a ret. This is very clever because like basically we return back to like the original target address. But if the CPU wanted to speculate, it goes only on like endless loop. This endless loop composed of pause and jump on itself. It could be even like a memory barrier. It's not needed that like, not a memory barrier, sorry, a speculation barrier. It's not needed to be like that one. You can insert whatever you would like. And this like, yes, this is basically the technique. Okay, let's speak about how we implemented this stuff in Windows. From RS2, the Windows 10 Creators Update, we have introduced something called the DVRT. The DVRT is like the dynamic value relocation table. And it was used originally for like moving the PFN database and the page table. So it means that like every time you boot up your computer, basically the page table and the PFN database are on different like position in the virtual address space. How did we do this? We did basically the OS need a way to track every like pointer that is starting inside the anti-kernel binary. So for doing this, the compiler emits like an image dynamic relocation data structure for every like static symbol. This data structure contains two things. First, the pointer that, as we can see, the pointer in kernel mode have the first like 16-bit set to 1 because start with FFF. And the second one, the size of the entire like structure, because this structure is followed by an image-based relocation. This array of image-based relocation basically describe each page of like the binary. And after this is followed by the 16-bit value that contains the offset. So basically, what happens when you switch on like your computer and the WinLoader like give the execution control to NT-kernel? Basically, at memory manager phase -1, that the NT-kernel is still not initialized, doesn't know anything about, doesn't have initialized anything. We are able to randomize the location of the target VA regions, like for example the PFN or like the PFN database or the PT table. On the right of this slide, I have put like a sample. If you reverse it with IDA, you will see that like there is like FFFF6800, that is like the page table base, if I don't remember wrong, or if I'm not making some confusion. No, yes, it's that. And so basically, we apply the fix up to every static value that is present in the binary. So I did this introduction because like we found that, of course, every pointer in kernel mode has like the first like 16-bit set to 1. So what we did is that we put like, instead of the symbol field of this data structure, we put like a value that is like, is not a pointer, is like a standard value like 1, 2, 5 or whatever. And at execution time, we recognize that the symbol is not like a pointer, so we know that it's something else. So in this case, there is still like the image dynamic relocation and image-based relocation data structure. But after that, there is an array of 16-bit or 30-bit values. That is not like is not an offset, basically. Each value describes the branch instruction. So, after applying this to every indirect branch in the kernel, we have identified that basically like there are 3 kind of like branches that we needed to like take care of. The first one has like branches that happens thanks to the imported addresses. So when like a binary in kernel like need to like call another function in like another binary, use an imported function. So there is a pointer in the IAT, the import address table, and then we call that pointer. The second one is indirect branch. That are branches that use a register, like for example jumper IX, call RCX, or whatever. Usually these like kind of like branches are used to like call external like function that reside in another binary, and usually are used a lot in case of C++ vtable, not in kernel of course, but like to make an example, the C++ vtable uses like move the pointer in like a register and then call a registers. And then we have like identified the Switchtable Retpoline that are basically indirect branches that happens on the same binary. Okay, yes, we are on time. So here is the slide that shows the imported address Retpoline. So basically, on the top of the slide, you can see that like there is like the original indirect rel32 call on IAT entry. So this means that like the call must first resolve the pointer, push the return address, and then jump to the target function. I would like to show that in the new kernel, we have put even like some padding after the call, because we need to be able to apply and not apply the Retpoline dynamically, based on the target OS. Yes, the target function address is stored in the IAT entry that is generated on the fly by the loader, basically. So, an important thing to say here is that like the Retpoline guard function need to do these things, simple things. First, check a bitmap, because in the NT-kernel we track every section of the driver that is compatible or not with Retpoline. So we have a bitmap. That bitmap describes as 1 bit set to 1 if like a 64K via range is Retpoline compiled. If both the bitmap exists and has a 1 in the particular point, means that the target is Retpoline compatible. So what we do is that like we call the Retpoline function and then jump directly to the target. Otherwise, if one of the two like condition is not true, we set the IBRS or IBPB depending on basically on the CPU architecture. We execute a memory a speculation bar instruction, and then we jump to the target address. In that way, we are sure that like we can't an attacker can like speculate on this, because the target address is not Retpoline compatible, but we run with IBRS set to 1. And on the bottom of the page of the slide, you will see like the data structure that is the 32-bit offset, basically. 32-bit like array. In this case, it contains the relative offset inside the page. So a page is 4K, and we need 12-bit for like describe the offset. A value that is set to 1 or 0 if the call is if the branch is a call or a jump, and then the index into the IAT. We saw that 19 bits are enough for indexing the IAT. Indirect branch Retpoline. Even here, it's like similar to the previous case, but it's used for indirect branches that are like target another function, another like code that resides in another like module. It's used for generic indirect branches, and we can support indirect branches that are non-CFG, like a simple call to RIX, or like even indirect branches that are CFG compatible, so that basically there is a CFG check function. And yes, as before, the top of the slide represents the original like situation, and the bottom, the situation where we apply the Retpoline. There is still padding around because we need to be exact when we apply the new direct roll32 call. So the guard function in this case is similar to the previous one, meaning that like basically like it does the same, almost the same as the previous case, but it checks even the CFG like bitmap in case of like we have indirect branches that use a CFG. Basically, we do two things. If the target is not in the CFG bitmap, we bug check the system, because this is a security feature, so we need to do that. If the target is not Retpoline compatible, we call the target using with IBRS set, like before. We support only RIX register because we found out that the compiler is able to emit like to transfer all the indirect call using the RIX register. Yes, the data structure that tracks this, it's pretty similar to the previous one, instead of the fact that instead of using the IAT index, we emit some other stuff, like if the indirect call is like using the RX prefix, or if as is CFG or non-CFG. Last is the switchtable Retpoline. The switchtable Retpoline is the easiest one, because basically it's like they are used when you have like a switch statement in C++, for example. So there is like a jump that goes directly in the same binary. In this case, like as you can see, there is nothing very particular. We have like an indirect jump, and then we replace with a direct roll32 call to the Retpoline switchtable guard function. The switchtable guard function does nothing interesting. It's basically only apply Retpoline, because we know that the target is like in like a Retpoline compatible like binary, so there is no need to do anything else. And even like the array after the data structure is like pretty easy. It's like 16-bit. In this case, we support all the registers, so there is no need to change anything by the compiler. Okay, one important thing to say here is that after we have implemented the first like Retpoline, we were still not happy about the performance, because like we were like thinking that we could do more. So we have like analyzed the problem, and the problem resides especially on the imported functions. Means that we were losing some time in when the driver were calling like imported function. So we thought about this a bit, and we found out that after basically the import address table has been like populated by the loader, there is no motivation why we need to emit like still an indirect call. So basically, like you need to imagine the loader that basically like compile the IAT. We apply Retpoline, And then we designed something that is called the import optimization. Because if you think about the indirect call exists for important function only because you need to check the IAT. But when the IAT is like filled, there is no way. I mean, it will not change. So why buffering about like using indirect call? We can emit like a direct call or jump. In this case, we can see the new code about the that uses import optimization. As you can see, there is like a direct rel32 call. Means that the function is called directly, and there is no speculation feasible in this case. So, and we found that like basically the mission was complete because the performance was like improved a lot. If you have seen, we are still saving the original pointer. We will see in a while why we do that. Okay, let's speak about the details about the implementation. So basically, when you start your computer and the execution control goes to NT-kernel, the phase -1 of the memory manager initialization check if retpoline need to be enabled. At this stage, there is nothing initialized. There is initialized only few boot structures, like the processor control region, processor control block, and DPC stack, and not many others. So basically, the function KA determine retpoline enable decide if not enable or not the retpoline and import optimization based on mainly two things. The first one is like the if your CPU support the hardware speculation control features. I mean, if your CPU has IBRS basically or IBPB. Here I've written that AMD as Intel uses different model-specific register and CPU ID classes. But basically, this is important because if you think about that, if the CPU is not able to protect in hardware, we have no way to protect for external code. So there is no way to enable this feature because, like, we can protect only half of the problem, and so we disable the retpoline and import optimization. Another thing that like this function check is the memory manager feature setting registry value. In that way, you can like control if to manually enable or disable retpoline and import optimization. Okay, so basically what happens? After like the previous function have decided that like the retpoline must be initialized, still the memory manager phase -1 is initialization. Basically it does two things. First, perform the SLR on dynamic VI regions, like as we have seen, the page table entry, the page table and like the PFN database, using the DVRT like data structures. And second, it calls like the retpoline initialization function. So basically, what do? We analyze each like DVRT table, and like we skip the one that are for how do you say, for like the dynamic VR regions. We detect only like the DVRT like entries that are related to retpoline. We parse them and we apply retpoline and for each indirect branch of NT-kernel and of all. After that, we capture the IAT of NT and all. As you probably know, both NT and whole import for like very few modules because like they are the kernel they are the core of the kernel. And yes, we apply even import optimization. I need to let you know that like at this point the bitmap doesn't exist because the memory manager has no idea how to create a sparse bitmap. So this is not a big deal because like the worst things that happen if we call like something that is like indirect branch, we set up the IBRS. So it's not a big deal. Late at phase 0 of MM initialization, basically there is the retpoline sparse bitmap creation. So in this bitmap has two characteristics. First is sparse, so we don't consume a lot of user memory, RAM memory, because if it's sparse means that like only the needed region of the bitmap are actually allocated. And the second is that each bit of this bitmap represents a 64 kilobyte VA space. Because we have noted that every section in the PA image is like aligned to 64-bit normally. So another thing that I need to say is that the phase 0 of initialization function initialize even like the synthetic function table for the virtual unwinder. Because basically we found like a problem that if you have a context switch, if you have an exception on like the Retpoline trampoline code, or even on the new Retpoline function call, the virtual unwinder have no idea how to like unwind the stack. So basically bad things happen, blue screen of dead, or random error basically. Here is another important thing, the boot drivers. At phase, basically the Windows loader has like load each boot drivers in a contiguous and randomized virtual address space. So after, when NT take like control of the machine, these boot drivers can be virtually or physically relocated. But how we did that? We did in a pretty, we think at least that we did in a pretty smart way, because like basically the Windows loader, when it maps each boot driver, and when I say map, I map and read, but not execute. We also have a code page at the end of like each boot driver. This like code page is not mapped anywhere at the Windows loader initialization time. The memory manager phase 0 at initialization time basically like maps this page to the actual Retpoline guard function. This guard function that implement the bitmap check and even like the Retpoline are like located in a particular section of the NT image that is called the Retpol. So after this, like the memory manager applies the Retpoline, update the bitmap, and then at the end applies import optimization on like each driver. I'm speaking about boot drivers. Late at phase 1, the NT kernel start like each boot drivers. One important thing to say is that, like here, the boot drivers, for the NT perspective, are only a chunk of memories. They are nothing else. They are not bucketed by any section or by anything. So this explains why you can like rename or delete your boot drivers from like a live system. But this is important because it's a huge difference. Okay, in this slide, like, I have like drove like a scheme for each boot driver. As you can see, like each boot driver still has PE header, section header, each section. At the end, there is a digital signature and the Retpoline page. The red one, the Retpoline page, is mapped on the same PFN, so we don't like consume like memory. This Retpoline page is only a page now, but in the future can become more, can become even 2 pages or whatever. It's not like a big deal actually. Okay, the same principle of allocating the Retpoline page at the end is applied even like for image-baked driver. Okay, speaking about image-baked drivers, are drivers that the user can start with SC start whatever, or like the NT kernel can start after when the system is completely initialized. This image-baked driver have the peculiarity to be like baked by like a section object. So we apply Retpoline import optimization in 3 cases here. First, when the code integrity module validates each page and the shared page are brought in memory. Second, by the page fault handler, when a prototype PT fault happens, so means that the shared page has been like paged out of the disk. And third and part, very important to say, is that the fix-up must be applied and reverted every time, because for various problems that we will see in a while. One of the problems is that if you think about and you start a driver using SC start driver or like your preferred method, and then you map the driver using like a section object in user mode, what can happen? It happens that basically inside the kernel there is the image section control area that has all the subsection and segment data structure and tracks the shared page. Basically, the new control area, the data section control area, the pages are copied from the image control area. So you can imagine that we need to revert Retpoline and input optimization, because otherwise bad things happen and like you have like a security vulnerability. This slide has been taken from Windows internals. It's very complex. I don't have time to explain, unfortunately, but this is how it works. So returning back. Yes, so basically, the important things to remember here is that we apply import optimization and Retpoline on the shared pages that are mapped by prototype PTEs. So when you try to access, if you remember, when you try to access shared page, there is a fault in the kernel, and then there is a new page that is allocated, and the shared page is copied in the private page. Okay, I'm on time, yes. Another thing that we did is that implement this stuff on the secure kernel. The secure kernel implement credential guard, implement device guard, and is used a lot of times for the new security features. So we found that like if we enable secure kernel without enable HVCI, there was not a huge difference, because like the memory manager in NT-kernel was the one that was responsible in apply Retpoline and input optimization. And secure kernel was not used a lot in this case, so there was no difference. The huge difference resides in when you enable HVCI. Because when you enable HVCI, the normal kernel has no way to touch executable pages. This is by design, because it's the protection. Basically, in the SLAT, in the second level address translation table, there is not the writable bit set. So only the secure kernel can touch the executable page. So what we did is that we implemented from scratch Retpoline and input optimization even on secure kernel. One big difference to say is that in secure kernel, we don't keep track of Retpoline using a bitmap. This is because a secure kernel has only idea of protected images. So means that like an image should be like Retpoline compatible or not. There is no other like differences. So we put a bit in the secure image data structure that the secure kernel has to keep track of the protected like binaries. Okay, as you can see, here are the implementation problems that we faced. There are a lot. I don't have any time to explain all of that. Basically, I can say only something. For example, like an example was like the virtual stack Unwinder. We had like some problem about the boot drivers relocation, and we have even some problem because basically when like the NT-kernel in the beginning was relocating the driver virtually, maybe a driver could be like 4 GB far from another one. So we couldn't apply import optimization because, as you know, the DirectRL32 like call or jump uses 4 GB window, so we were screwed basically. So we have like problem with the check image debugger extension because that was extracting a lot of problem in Retpoline like fix-ups. We have a problem in driver verifier because when you enable driver verify, you need to think that if you enable on the fly, there is like a modification of the IAT like entries, so the driver can call a particular like checking function instead of like calling the standard function. We have a problem with private fix-ups, and we have a lot of synchronization issues, for example. I don't have time to explain any of this, but I can show you a funny slide at least. So basically, a long time ago, like when I was speaking with Alex, he told me that like people after like touching the MMM in Microsoft usually like pray that all will continue to work. When I was like implementing this in SK, basically I think that I have not prayed enough because as you can see, I have exposed for the problem that I was describing all the relative offset. When you basically you take the driver that is loaded, you map the same driver in user space, and you were extracting all the offset. So as you all probably know, this is a bypass, a big bypass, and a big problem. Of course, the problem was fixed now. This is a lesson that I've learned, basically. Okay, I have a live demo for you. If I'm able to like do that. Can you see? Yeah. Okay, as a preface, this is like a test version of Windows that I have installed. I have compiled and installed on my own system. So it should not crash, but if crash, please forgive me. So first of all, this is an application that a debug application that I wrote for testing this. You can see that like I can't show you. Damn. No, just let me. Yes, basically, if you can see, there is like Retpoline and input optimization enabled, right? So, second things to do is like to open a debugger. This is live debug of my own system. So, check the loaded module, if I can see that. Yes. Let me see. There is a lot of like modules loaded, of course. Let's take one random. I don't know. Let's take disk, for example. Do you like disk? So let's parse the DVRT table. Damn. Let's put even a base address. In that way, our calculation will be much faster. Where is disk? This one. And then create an output file. I am Italian, so I named my file ciaobeppe.txt. So, as you can see, the DVRT included a lot of imported, like, come on, I can't see that, just a moment. A lot of imported, like, Retpoline fix-up. And at the end, if we are lucky, we see even, like, yes, indirect Retpoline fix-ups. So, basically, to show those, we can just do this. If we are lucky and the code is not paged out, yes, it's not. In this case, you remember that like import optimization was enabled, right? So in this case, you can see that, I don't know why you can't see because this stuff doesn't work, but I will show you without zoom. As you can see, like these are a relative direct call. So it's not imported anymore. You can see, guys? Okay. So means that the import optimization is working correctly. So let's check another one. Let's check an indirect Retpoline fix-up, like the one with a non-CFG indirect branch. So let's take this address, go to the debugger, and then if we are lucky enough that it's not paged out, yes. Instead of like being like a jump RAX, jump RxCX or whatever, there is like a jump on a function. This function is the Retpoline guard. Apart from like the strange like name, because of course I have not loaded the symbol, but this is that was by design. This is the check of the Retpoline bitmap. Then there is like the calculation of the exact bit, and then there is like something else, like a direct call of like Retpoline like function, or like the code that set BRS. Yes, here is the Retpoline like stuff, because we can see like that there is like even the elfence, and then at the end you should find the end of Retpoline, this one. So means that it works. I wanted to show you that in this system there is even secure kernel that is enabled, and and HVCI is enabled. So means that like all the system works. So returning at the presentation, some conclusions. Here is the way for you to detect and retpoline and input optimization, the unofficial, non-official way. You can use like the native ZW query system information with like the speculation class, and that's it. It's only 2-bit, very easy, very straightforward. This is the proof of concept that I have detected that all works good. And then final thoughts. So basically, in this talk, we have like find that retpoline is an effective and fast way to defeat Spectre v2 without losing a lot of CPU performance. An interesting fact is that we found that with import optimization, the system is faster, even in normal retpoline environments. So we are trying to always enable that, regardless of retpoline. And this is very great. It's a good like achievement. One thing that I need to say is that implementing this technology from scratch was far from being easy. So it was pretty complex, but we did it. You can try it if you download the latest Insider release. Okay, some acknowledgement. I'm pretty new in the team, so I need to thank my team because like they were like very helpful and like they helped me a lot. So I think that I work in a great team. Thanks for that. And then I wanted to even like say thanks for like the three master of Spectre and Meltdown that helped me to like an understanding like Spectre and Meltdown in a correct way, especially Pedro, that has helped me a lot on understanding the basics. Last, the VC compiler team, because they have like implemented the retpoline in direct in the compiler. We have 3 minutes for any questions, so I was like on time.
For the retpoline itself, that endless loop, why did we choose that as opposed to calling something to disable the speculative execution or branch prediction?
Okay, so basically the example that I did it was taken from the original implementation of retpoline. You can choose to put whatever you think that is better. I mean, even like a speculation barrier is great. So you can do like insert whatever. Like we decided to do that because like for the speculation, like I mean, because when you return like when the CPU speculates, at the end do nothing. That's why we rendered like the speculation useless. That's why I mean you can put an endless loop, you can put even like a bad instruction, you can put even a memory barrier, or it's not a big deal actually at that point. But the original design of retpoline was like inserting like an endless loop. Sorry, I can't hear you. I think that like the microphone doesn't work. Okay, now it's better.
Were there any smart ways you tested coverage across all the processors, since you know this is really close to all the processors and Windows would be running on so many different processors? Did you have to do anything more than usual to test the coverage?
So are you asking if how we test on different processors, right?
Yes.
This is a good question. I can't reply now in 30 seconds, so we can think offline about that. But this is a good question, actually. Okay, if it's all.
All right. Thank you, Andrea,
Thank
for
you
that
for
great
attending,
chat.
And